full 10%, that's quite a large portion for anything in science to be considered significant. And some people point to that as a flaw in our current understanding of things. Next slide. All right, so we're going to get away from the weeds some for a minute. And we're going to go to the first question of the night, which is actually, full disclosure, not a question any of you asked. I did 2 events similar to this in the last several years. And the first time we did it, one of the students asked this question, and this is my favorite question anyone's ever asked me. And it's a great launching point for what I want to talk about next. And that is the evidence that I see in nature for God. And so the question is this. God seems to violate causality as well as he seems to violate Occam's razor, which is simply a good matter, or a hyper-intelligent, immortal, omniscient, omnipotent being. The kid who asked this question talks like this all the time. It's awesome. I love it. So a lot of terms to define here. I'll run through them quickly. Causality is simply cause and effect. Everything that happens has to have a cause. Everything that exists has to have a cause, a progenitor, or something before. Occam's razor is a philosophical idea. Let's get that one for a second. Which is simpler than a matter. So, as you would expect, Big Bang, or a hyper-intelligent, immortal, omniscient, omnipotent being, all-knowing, all-powerful God, obviously is what he's hinting at there. Go back to Occam's razor. Occam's razor is a philosophical idea, which Sam Harris did not come up with, but is probably most famous for promoting. And the idea is that usually the simplest explanation is the most reasonable explanation, and most likely to be true. So if you came in to the room and you see the circle drawn on the whiteboard, the most reasonable assumption to make is that Steve or I or someone else who was here before you drew the circle on the board. It would be less reasonable to assume that someone came, drew the circle on the board, and then left for the night. It'd be less reasonable to assume that we trained a monkey to come draw a circle on the board and then left. That's the idea of Occam's razor. Now, it should be pointed out that this is not a law of nature, and that oftentimes in nature we do not see this panning out. And I would love the person to say the simplest solution is the best solution to come do my homework for me next time, because that is not always true. But it is a good idea, and you can see why that idea has been used to poke holes in all kinds of things that people believe scientific and otherwise. So, how do we address this? Next question. Well, God does violate causality. He does. The idea of God is that he is an immortal being that not only immortal, it exists outside of time and space. That absolutely violates causality. But so does any idea of the start of the universe, including the Big Bang. So as I explained earlier, the Big Bang is currently understood to be a rapid expansion of something smaller than an atom into the current universe. Well, we have to get into semantics here for a second, and this is what you find as the beginning of everything. Because in physics, space and time are very much real, tangible things. Not only are they tangible things, but we can manipulate them. Well, we can't. We don't live in Star Trek yet. But stars manipulate space-time, planets manipulate space-time. Earth right now is bending space-time very slightly. The sun is doing it more so. Black holes, which is a concept I'm sure all of you are familiar with, are seemingly holes in space-time. That's where the term comes from. And the math actually gets very weird around black holes and suggests things that you're uncomfortable with about the universe. So if you're suggesting that the Big Bang is the beginning of everything, and that nothing existed before that, well, then nothing would include space and time, which eliminates any space and time for your event to take place to begin with. So that's a problem. And if you want to say, well, nothing means empty space-time, right? Think of a blank, dark, black room, right? That was all it was. Well, that's a problem too, because then you have space and time, and therefore you don't have nothing. You have something. Where did the space and time come from? Those are two things. Yeah.
Is space-time just the concept of space plus time?
Yeah, so space-time is, you'll see a lot of times explained in sci-fi shows as a fabric, and that is really the simplest explanation of it. is that gravity is able to manipulate the fabric of space-time. So the classic idea that we have, now, can I come back to this later?
Yep.
Okay, I'll come back. That's going to lead us down a really good tangent, but it will be a tangent. So I'll come back to it later, I promise. All right, so with all that being said, modern cosmology, at least in my estimation, requires as much faith as faith in our moral omniscient being.
One thing I'm just going to ask is, don't some scientists not necessarily believe it's the beginning of everything, it's just as far back as we can know?
Yes, which does not solve causality. Yeah, because so a popular theory that's arisen in the last 10 years or so is that there are multiple universes, and you can think of them as bubbles. So if you're trapped in a bubble, you can't ever leave your bubble because you're in the bubble.
Yeah.
But if you have two bubbles that run into each other, then you can form a super bubble, or sometimes we'll form a third bubble. I'm not naming what the Big Bang was. Where two of these bubble universes colliding and forming our universe.
Yeah.
Well, that doesn't solve anything. That puts you right back where you started of, well, where's the other universe?
Well, I guess I'm more on the question of it taking as much faith to believe in God, because not necessarily causality, but more of just saying, well, we do know this happened, I don't know before, but does it
Sure.
require faith to believe what we can show evidence of?
Yes, absolutely. All right. So we're going to go on this for a minute or two. So to illustrate the point of cosmology requires as much faith as that, this is something you'll hear frequently from people like myself, and that is that the universe is simply too finely tuned to be an accident. We are, as scientists, trained to look at numbers and data all day long. And if you have any number that is smaller than n.001, chances are you just could estimate that as 0. And ultimately, we don't have a number to define the total probability of existence, but whatever that number is, universally agreed upon, is a really, 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 really big number with lots of zeros after a decimal point, and then a 1. So, to illustrate this point, we're going to go to the next slide. Next several slides, actually. And we're going to talk about the placement of Earth and how absolutely, unbelievably fortunate we are to live where we do. So, you live here. Maybe. You do live here. This is an artist's depiction of the Milky Way. It's not a real picture of the Milky Way because we can't take a picture of it because we're stuck inside of it. So you can't take a picture of something you're stuck inside of. If you want to try, feel free to try to take a picture of the outside of Brookside right now. Not going to go very well for you. But this is a depiction of the Milky Way. It's a spiral galaxy with a bar in the center. It's called a barred spiral galaxy. Astronomers are not creative people. And this is immediately advantageous because there are multiple types of galaxies. There are spiral, elliptical, and irregular galaxies. And spirals formed, we believe, the quickest after the Big Bang, which is good because that means that you have a lot of time for life to occur places. You also have the advantage of being in a stable galaxy. So the Milky Way is 4 galaxies. Lots of galaxies are merging with other galaxies, or being run through by other galaxies, or being sucked up by another galaxy, and all kinds of fun things. Well, it's very interesting to study. You wouldn't want to be in those places when that happened, because you would be dead. So, next slide. Not only do you live in the Milky Way galaxy, but you live approximately here, about 2/3 of the way out from the center. You live in something called the Orion arm, or Orion spiral arm. There are multiple of them in the Milky Way. We're actually not sure exactly how many, but we do know we live about 2/3 of the way out from the center. And that's good. Why? Well, because if you're in the center, there's the most stuff in the center. And that's bad, because the more stuff means more radiation, means more things. Think of it as a shooting gallery. If you are playing a game of paintball and you don't want to get shot, where do you go? The outside of the course. Because all the people are running towards each other in the center of the course. So you want to avoid that as much as possible. That's good. We're in the center of the galaxy. We are safe from the utter chaos and supermassive black hole at the center. You don't want to be out here, though, at the outer edges, because in the outer edges, typically, you're not going to have the right conditions for the right kinds of stars to form that you need to live around. Next slide. Speaking of, you live orbiting quite possibly the most boring star in the universe. And I say that in that the most exceptional thing about the sun is how boring it is. The sun is extremely stable. It is about 5 billion years old. It's middle-aged. It will live for another 5 billion years before it blows up. We will all be long gone by then. It is a medium-sized, medium temperature star that is extremely stable. Lots of stars pulse. They literally grow bigger and smaller. Some do that within hours, some do it within days, some years. But all of that is going to cause massive problems with any sort of life trying to live around it. If we suddenly increase the size of the sun by 1/3, you would die instantly. If that happened on a semi-regular basis, there's no chance for any sort of life to form ever around any star. So, sun, extremely boring, great stars to live around. We also know that stars are nuclear factories. Stars are powered by nuclear fusion. Essentially what happens is you have a gas cloud that for a variety of reasons can condense and form a star. The universe is composed of 99 or 98% hydrogen with a little bit of helium, and then less than 1% is every other element you've ever heard of. So the universe, astronomers often like to joke that there are only 3 elements in the universe: hydrogen, helium, and everything else, and we enjoy annoying the chemist when we do so. But this is what stars do. They eventually get big enough that the temperature at the core of that gas cloud gets hot enough that nuclear fusion starts, hydrogen forming the helium. Now, stars will do that, and originally when that happens, a star will do that for so long, and it will form progressively heavier elements: hydrogen to helium to carbon to oxygen to nitrogen to all of that. When stars explode, you get most of the heavier elements that you are familiar with that occur naturally. Those elements are the ones that you are made of. The most common element in the human body is carbon, along with nitrogen and oxygen. So, if you're going to live around a star, you want to live around a second-generation star. Because if you live around a first-generation star, a star that has none of those heavy elements already present in that cloud, then you don't have it. Because there's no carbon, there's no nitrogen, there's no oxygen, there's none of those things that we need. So, from that gas cloud, the sun formed. It is a second-generation star, thus making life possible. And from the remains of that cloud, all the other planets and all the other things in the solar system would have formed. Next slide. But if you live around the sun, it doesn't mean that you're actually going to be alive, because essentially you have to be the right distance from the sun. Astronomers refer to this as the Goldilocks zone. Not too hot, not too cold, just right. Now, for most stars, that is a relatively narrow strip of distance. The distance between the Earth and the sun is defined as being 1 astronomical unit. It's 93 million miles. But again, this is 1 astronomical unit. Venus is at 0.75, and it's outside the Goldilocks zone. Mars is at 1.6, and it's just outside the Goldilocks zone. Some will argue it's within the Goldilocks zone, but regardless, it is right on the edge. Which means, if you do the math, you have a very narrow strip of potential places for the planet to be where we are comfortable and conform as we know it. And this happens to be where the Earth is. Next slide. But we're not alone in our solar system. We have several outer planets, including one really big one in Jupiter, which is the king planet. I guarantee that none of you realize how big Jupiter is. Jupiter is more massive than all other planets combined. It is huge. And what effect does that have? Well, there's a lot of crap floating around our solar system, all of which wants to kill us, and all of which is attracted to us because of our gravitational pull. Jupiter's gravity is so immense, however, that it stabilizes not only a lot of the asteroid orbits, but the entire solar system. So, on the screen is a GIF of what are called Trojan asteroids. These are part of the asteroid belt. The main asteroid belt is here between Mars and Jupiter. Then you have these Trojan asteroids that share the orbit with Jupiter. And what you're seeing there is the effect that Jupiter's gravity has. It suspends them and keeps them in orbit with Jupiter. And if you remove Jupiter magically from the system, all of these, most of them would go careening in towards the inner solar system, and then Earth looks like the middle of a pinball machine. And that does not end well for us. Some of you may remember in the room in the late 90s, I forget when the 90s, might have been the early 90s, whatever, before I was alive, there was an event called the Shoemaker-Levy 9 impact. And it was an asteroid that was coming towards the inner solar system, probably would have missed Earth, but it would have been close, and it was a really large object. And if it would have taken a turn for the worse, it would have been an absolutely devastating impact for the planet. Fortunately for us, it got too close to Jupiter, and it impacted Jupiter. But the object was so big, it broke up into 9 parts when it hit, that it actually poked holes into Jupiter's upper atmosphere clouds. And you could actually see them through telescopes for months. Typically, you would never see that. It would take immense objects to actually be able to see the damage done by an impact like that around another planet. And you can see these clearly during that event. And that's just one thing that's happened. Next one. Ooh, go back. Not ready for that. All right, so to give you some sense of scale, I'm going to do the following. Jupiter is very big. I've already told you that. This is Earth. It is the size of a bouncy ball. I picked blue because that seems appropriate. I will return it to the physics lab tomorrow. If we scale Earth down to this size, to give you some concept of what I'm about to tell you next, you need to have an idea for the scale of not only the solar system, but the universe as well. If this is Earth, that's the diameter of Jupiter. It's really big. It's 11 times the diameter of Earth. And if you are familiar with the Great Red Spot on Jupiter, which I'm assuming you all are, I've got markers over here. The Great Red Spot, which is essentially a giant hurricane happening on the surface, is so large that it is actually about 3 times the size of Earth. It is a hurricane that is happening on the surface of another planet that is 3 times the size of our own planet. That's really big. All right, I told you Jupiter was by far the biggest planet in the solar system, and I told you the Sun was a medium-sized star. So this is about 1 inch wide. Jupiter is about about 13 inches wide. Do we have any guesses as to how wide the Sun would be on this scale?
8 feet.
Anyone else?
Bigger than the room.
Not quite. 8 feet's actually pretty close. If I stood here, or sorry, if you look here as being the start of the Sun's diameter, we would be here. This is a distance of about 10.5 feet. So I wanted to bring a ball to illustrate that. I didn't have one that size. So imagine a ball like this one that extends from me to the music stand, and then of course it's a ball, so that also means that if it's sitting on the floor, it's going to extend up to the lip here, the bottom of the projector screen. And then it's going to extend radially outward that wide as well. If you combine all the mass in the solar system, the Sun, the planets, the asteroids, the comets, the dust, all of it, the Sun makes up 99.98% of that mass. It is absolutely massive, but it is not in any way, shape, or form a big star. So, if we wanted to look at one of the largest stars that we know exist, it's called Canis Majoris, the Big Dog Star. How wide do you think it would be? Any guesses?
1/4 mile.
Keep going.
10 miles.
Not that big. 2.87 miles.
1
Wow. That is insane. Again, the Sun, 10 feet, largest star in the universe, or one of that we know of, 2.87 miles across. That is so big that if you put it where the Sun is in our solar system, it would extend, the radius of the star would extend out to Jupiter's orbit. Just about. It's absolutely massive. All right, so that's impressive. I mentioned, though, that's size. Now let's talk distance. So if we wanted to go to Alpha Centauri, which I mentioned earlier, the biggest or the closest stellar neighbor to us, We go 4.5 light years.